In my long term, I studied the effects of temperature on the cohesion of water. A little bit of background information on polarity. Polarity is the property of water that gives the molecule a small charge. So hydrogen atoms have a small positive charge and are very small molecules. And oxygen atoms have a positive charge and they are a very large molecule. So, since the oxygen is so much larger than the hydrogens, it's going to leave the molecule with an overall small negative charge. This allows it to attract and bond to other substances, which is called adhesion, attract and bond to itself, which is called cohesion, and hold more weight than it has itself, which is called surface tension. So the question I'm asking is, how does temperature change water's cohesive property? My initial thoughts were that heat makes molecules vibrate. The hotter the molecule, the faster it moves, and the colder the molecule, the slower it moves. As we can see in the picture in the bottom right, gaseous substances have molecules that move in straight linear patterns and bounce off of other molecules or other objects. Liquid substances have molecules that move in sort of flowy, free patterns, bouncing off of each other and the container they're in. And solid substances have molecules that are in fixed, rigid patterns and do not move besides vibrations from heat. So my thoughts were that the closer it is to being solid, so the colder that it's going to be, for water at least, then the tighter the molecules are going to be holding together. So my first claim was that the more heat, the weaker the cohesive force would be. So my round 1 setup is that I was going to measure temperatures by increments of 10, from 20 degrees Celsius to 70 degrees Celsius. I did this using a steel temperature probe and graphical analysis. And then once the water was heated up to the temperature I wanted, I used a plastic micropipette and filled it up and then dropped it onto a penny and counted how many water droplets the penny could hold, with the idea that the more drops it held, the more cohesion it had. And as we can see in the data table in the bottom left, generally, as temperature went up, the drops went down, but there was a weird trend, which is easier to see in the graph on the next slide. So, as I said before, there was a weird trend between 20 degrees and 40 degrees. The data had a dip and then was a smooth downward trend for the rest of the data. So I didn't know why this dip was happening, and I thought it might be just an error that I made. So for the next round, I used the same procedure, except I did 3 trials for every temperature, which would hopefully balance out the human error I thought I was making. However, there was still the dip trend in this data, and I noticed that between the trials, the drops it was holding varied a whole lot more than it should have. So I needed to figure out what this dip trend was and why there was so much variation in my data. So I had human error, obviously, because no one's perfect and there's always going to be a small error from the experimenter. And there's usually a small tool error from any tool I was using, which was the pipette in my instance. But if I was applying different amounts of pressure every time that I squeezed the pipette, all of the drop sizes would have been different. And, as we said when we were analyzing polarity, liquid has molecules that move in flowy patterns. So as it gets hotter and hotter, the molecules are going to move faster and faster, and the substance actually expands. So combining these two things means that I was actually varying 2 things at once, the temperature and the volume of the drop. So my second claim was that the inconsistent results were due to the inconsistency in the size of the drops. So at this point, I reached a couple setbacks. Since school was canceled, I ran into a few problems. I didn't have an accurate way to measure temperature at home. I also didn't have a very accurate way to consistently drop water, and dropping onto a penny was going to be very difficult since I couldn't control when or where the water droplets fell. So my solution to the temperature problem was that I was going to use the idea that water heats up from 0 degrees Celsius to 100 degrees Celsius on a linear scale. To solve the problem of consistent dropping of water, I was going to use gravity to pull drop off of a string, and to solve the location of the drop problem, I was going to use a string to drop water onto a paper towel as opposed to a penny, just so that I wouldn't miss or overflow or miscount. And then I was going to measure the diameter of the drop on the paper towel. So pre-experiment, I had to play around with a few things to decide the best way to do the actual tests. First, I had to figure out how long it took the water to rise by 10 degrees Celsius. So in the picture on the bottom left, I had a small clear container filled with water that I had freezed overnight, and the red thing is a pan that I was heating it up in. So I put the frozen block of ice into the pan, and I timed how long it took to go from freezing to boiling. And then it took about 5 minutes. I did it 3 times just to ensure that it was accurate. And each time it took 5 minutes. So 5 minutes is 300 seconds. And as I said before, it's a linear scale. So 300 seconds divided by 10 is 30 seconds for every 10 degrees. So this means it takes 30 seconds for the water to rise by 10 degrees. The second thing I had to figure out is whether or not I wanted to drop water off of a string or a fabric strip. So the picture in the middle, on top is a white fabric strip I just cut from some scrap fabric, and on the bottom is a string that I folded and twisted several times to make it a little bit thicker. And then I soaked both of these things in water and dropped them onto a napkin, which we can see in the 2 pictures on the right. And then I found that the fabric strip held a lot more water and it was easier to get drops off of, and sometimes the string didn't get up to 3 drops, which I knew wasn't going to work because I wanted to do 3 trials for each temperature in my test. So I ended up going with the fabric strip. So my new setup was that I labeled 8 pieces of paper towels from 10 degrees Celsius to 80 degrees Celsius, so I knew which paper towel I was supposed to drop the water onto. And then every 30 seconds, as I was heating the water up, I stuck the fabric strip in the water up to a line that I had drawn on it, just so that there was an even amount of water every time, and I let 3 drops fall off onto the paper towel. And then at the end of the test, I measured the diameter of each of the drops to the nearest 0.1 centimeter. And as we can see in the data table, the results didn't vary too much between the trials, so I thought this was going to be much more accurate than the other tests. And it was. It looked like my hypothesis was being proven true. As the temperature increased, the drops were larger. And I had thought this meant it had less cohesion as temperature was hotter and hotter, because if the molecules were holding tighter, the water wasn't going to spread out as much. But we did notice that as the temperature went up, the trials varied less and less between themselves, and the dots were closer and closer together. So we thought this might have something to do with area, because as area gets larger and larger, you have to have a bigger diameter to make area change. It's not linear. So I made an area versus temperature graph, but the dots still had that weird cluster trend up at the top, so I figured it was just because the area or the diameter of the drops were just more accurate up there. So the only thing I can conclude from these 2 graphs is that diameter and area were both larger as temperature went up. So my conclusions from my tests were that based on knowledge of molecular behavior and polarity, cohesion should decrease as temperature increases. However, from these results, we cannot conclusively say that cohesion is the reason for these trends. There's too much variation and room for error. So a couple confounding variables that I ran into, just to recap, is that as temperature increased, the volume of the drop also increased, which was causing me to vary 2 things at once. And second, it was more difficult to ensure consistent drop size and impact since I didn't have tools at home. Third, the rate of change for area and a change in diameter is not linear, meaning that as diameter gets bigger and bigger, it has to get even bigger every time you want to change area by that much. Fourth, the assumptions of having a disc-like area for water droplet does not take the cohesive forces into account, because cohesion actually makes it into a dome, as small as it might be. 5, the assumption that the temperature and time change on a linear scale is theoretically accurate, but I couldn't back this up with my own data. And 6, the dip pattern in the graphs is confusing and cannot be understood from this experience. Thank you for listening, and are there any questions?